Hey gamers, don't forget to like, subscribe, and hit the bell. So you wanna learn about networks, huh? Let me show you how this networks, yeah. We got edges, we got nodes. You need both of those to understand how this goes. A node is anything from you to me. This includes the leaves on a tree. Information is what it encodes. Without edges, this cannot flow. Networks, 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 Next are edges connecting you and me. Without them, we could not be. In the Slack or in the Zoom, internet connections are edges too. Information like particle collision. We can recreate the classical partition. Without edges, there would be no information flow. Without edges, there would be no place to go. Networks hold a close place to my heart. As such, this is just a start. I'm fucking here. Alright, enough of the funny business, enough of the goofs, the gags, the jokes, the laughs. This is time to be serious. And what I mean by this is that we're actually going to talk about networks. I'm not going to make a joke, a laugh, a gag. This is adult time. So the premise of this project is a Monte Carlo MC simulation on random graphs. But this really begs the question, what is a Monte Carlo simulation? Well, it's named after the location in Europe. I don't know the precise country that it belongs to, but it's a place in Europe. It has nothing to do with the place, it's just named after the location. However, a Monte Carlo simulation is really a numerical way to find out a property about an inherently random process. The premise is that a certain structure with the right initial conditions will have a random result each time, so if you aggregate the results for the random conditions, you will see that there is some inherent structure to the end result. Since there is usually no closed form solution to this type of problem, Monte Carlo allows us to arrive at what the closed form solution would look like if we were capable of solving it. This is particularly useful for transcendental equations. So we know what Monte Carlo now, but what is a graph? A graph is an array-like structure, speaking in terms of computer science, that encodes information about the system at play via network theory through information theory. These vertices, or nodes as we call them, are what encode the information, and these edges are what allow for information to flow from one node to the next. These edges in total m. So how do we combine the two? Well, there is a variety of graphs, but one type in particular are called Erdos-Renyi graphs after Erdos-Renyi. These are purely random graphs that take in two parameters: the number of nodes n and the probability that an edge will form between any two nodes p. Every time this graph is created, it's purely random. However, based on the initial conditions n and p, there are characteristics of the graph that should be approximately the same in large enough trials. As such, we can apply Monte Carlo simulations to confirm that these large-scale simulations agree with what mathematicians have derived over time. These can apply to average node degree, meaning how many edges are connected to it, and the number of edges. We can also apply this to entropy, but we'll get to that a little later. For now, the main focus is just developing networks, but entropy is a scalable module that operates on networks that reduces its eigenvalues and eigenvectors down to a single quantity. This quantity tells us the chaos or the randomness of the system, etc., etc. There are also many forms of entropy. In general, they take on the equation on the right. However, p of I can be really any function that sums to 1. There are 2 here that are accepted. The overall order of the system, meaning basically how connected it is without considering the number of communities or substructures. There's also the partition function model, which is more for community detection that detects these substructures. It's less for the order and the arrangement of the system, and more so to detect the connectivity between sets of nodes. So ultimately, what am I trying to do? Well, I want to use these methods to study general properties of random graphs. Then, after we establish the base case, in particular heteroserenity and another type of graph, which we'll get to eventually, stochastic block models, we can look at social data, like interactions between real people, or we can look at particle interactions through an analogy. The analogy being that if there exists an edge between 2 nodes and they are able to collide within a time span or a frame. The real limitation here is that the pi 0w kind of sucks, but we can reduce this data down to a smaller scale, and in doing so, we'll actually be able to operate on it. Dun 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 dun.